Whew, that's the hardest thing I've done all week. Okay, we'll do a do-over here. I know we've used a little bit of our time up. Chris Alexander, we've got our PowerPoint working. Those of you who are on WebEx, you should be seeing our screen. Wendy, you seeing the screen? Okay, so we'll get started on our merry adventure here. So most of you that know me who are on the call today, you know I love full-scale testing. Been doing this in the oil and gas industry since 1993 and have, for the most part, had a lot of fun. It's a great place to be. Obviously, this is kind of a scary time in our country right now and really world. But you know, the good news really at ADV is we've kind of been continuing to work with a lot of you. And so we realize a lot of you are at home. And we thought this would be a great opportunity just to talk to you a little bit about what we do. I think most of us are spending way more time doing conference calls than we ever thought possible. But we've learned how to do it, and I think that's a good thing. So this is kind of the agenda for today. I've got a few deep thoughts, a couple of philosophical things for us to talk about. Obviously, the focus today is to talk about full-scale testing and why are we doing that. And so I think a lot of you on the call you fall in two groups. A lot of you are pipeline operators. I know some of you have logged on. Also know there's a lot of technology companies, and there's also a few regulators. So, you know, in this pipeline world, which is primarily where ADV is kind of focused right now, there's lots of opportunities to do full-scale testing. And so we're going to do a little lab tour. We would love for you to come out to our place, but that's a little difficult to do right now. And so what we're going to do is we're going to put you through our lab. We don't have a video, but you can kind of visualize through some pictures. And then we've got case studies. And I know when I go to conferences, I always enjoy when presenters present case studies, war stories about things that they're doing. I tend to find that I'm far more interested in the presentation. So we've got a lot of case studies that we're going to be doing today to kind of walk you through and give you a feel for how does testing work in terms of evaluating technologies, but also looking at features and pipelines and those types of things. And we'll kind of wrap up with what we can do for you. So deep thoughts. I love to read, and a lot of you know Wendy Courtright, who kind of is our office manager and wears a lot of hats at ADV. She and her husband Brian bought me this book, Shut Up and Listen, Tillman Fertitta. If you live in the Houston area, which I know a lot of you do, Tillman owns the Rockets. He owns Golden Nugget Casino, I think, in Louisiana. And he owns a lot of restaurants. And so he's pretty well known here in the Houston area. So the title of his book is Shut Up and Listen. So I'll kind of work backwards because I'm an Aggie and we like to do things a little differently. So one of Tillman's concepts is that 5% of what you do contributes massively to the success that you have. And so I think about what we're doing at ADV. A lot of times if you've got an integrity budget, you're spending a lot of money digging, repairing. There may be a small amount, that you spend doing testing and analysis that really determine the overall success of how your pipeline's able to be maintained. So I think in life it's the same thing. You go into a lot of restaurants, everybody serves food, but sometimes it's the quality of the food and the experience that you had that makes you want to go back. So I think obviously Tillman's been extremely successful in business, so I think that's something we can learn from. Kind of going back to the top, if you watch the news like we tend to do at the Alexander House, there's a lot of discussion on models, and I think it's kind of funny. If you rewind the clock 6 months ago and you go to the latter part of 2019, my guess is most of the commentators on TV, if you ask them what a model was, they'd say, well, it's someone that you take a picture of. They had no idea what a model is. Everybody today, we're waiting on the COVID model to be right. So there's a lot of discussion on that. And in the engineering world, what modeling means is I'm simulating something that really happens. I'm feeding data into it. And as engineers and scientists, pretty much from the early part of our education, our entire math is built on building models. Well, this quote here, all models are wrong, but some are useful, is a very healthy position to take. Because what that means, if I start off and I always assume the model is right, then I'm going to get myself in trouble. I'm going to make assumptions that maybe aren't real. But if I feed data into it, I can get better at it. The other one is a new one I added from last week's presentation. There's no delusion like self-delusion. And sometimes I see this with technology companies as they'll develop a technology and they're excited about it, and then they'll come to the lab and maybe it doesn't perform the way that they want. And so I think it's very important for us to have a very objective perspective of what we're doing. And the third bullet there is a one I love, came from Ronald Reagan. I'm not sure he made it up, but he certainly made it internationally famous, and it's a trust but verify. And that's always a good approach to have when we do things in engineering. So here's kind of the whole gist. Why talk about testing? What's the reason that we're doing this? And as you go through this presentation, you'll see different facets of the kind of things that we do. But the purpose in testing is to make our models better. So if I've run an inline inspection tool and I get information about features, maybe I've got dents, I've got corrosion, I've got low frequency ERW that has seam flaws. How do I take all the information I've got on the ILI side and make decisions in terms of how I maintain that pipeline system? So when we talk about testing, what we're really doing is talking about generating data that we feed into these models. Even though our business is we primarily do testing, we do finite element modeling as well. It'd be great to me to test everything that we possibly can, but that's not very smart, and it's not the best way to do engineering. So what you'll see as we go through this presentation, we want to be judicious in choosing data that we get that feeds into these models. So I like graphs. Almost anytime I can get up in front of a group and I get on a whiteboard, I'm going to draw a graph. And so we came up with this acronym. The acronym is ICAD, and it's four words: inspection, categorization, assessment, and determination. So if you think about if you're a pipeline operator and you run an inline inspection tool, so you're doing the inspection part of it. A lot of what we talk about in the pipeline world, and really to be honest with you, almost everything that we do, especially with COVID today, we're talking about risks. I mean, it seems like a debate I have everywhere I go is, do we wear a mask or do we not wear a mask? And you got differing opinions. I'm not going to elaborate into this, but there's a certain risk level in everything that you do. I get in my car and I drive to work. There's a certain risk that I take in anything that I do. So the goal when we operate oil and gas facilities, specifically pipelines, we're trying to manage that risk. And so I get the inspection information, then I categorize it. In the pipeline world, we have these bins. So it's either corrosion or it's a dent or it's a selective seam corrosion, it's SCC. So these things, this information drops in bins. And I continue to be amazed at what the ILI companies are able to take all of this data and they drop it into these individual bins. And so what happens is my risk is still relatively high. I start moving down here. I start pushing that curve down. We talk about the curves all the time. So as I start doing modeling, which could be finite element modeling, it could be fracture mechanics, or I do testing to complement that, I start increasing my knowledge, which is what I feel like I'm doing a weather report here. But as I go to the right, I'm increasing the information that I know about a particular system. And so the end result is I'm able to take a higher level of confidence in how that's going to perform. So what I'm effectively doing is I'm pushing the risk level down all the way to the very end. If I've got a really good handle that I know I've got a dent and I know I'm going to see some fatigue cycling, it's only going to last 5 or 6 years, I want it to last 50 years, I do a repair. So a lot of the case studies you're going to see today, we're living in this world over here. We're doing testing to make sure that when we determine what we're going to do, we're doing it safely. And probably what I'd do is if there were a room full of people here, I'd probably stop and see if you've got any questions. At the end of the presentation, we've got a slide. You can download this from our website if you go to advintegrity.com. Those of you who are doing the WebEx, you might even want to log on there and go to the live stream because you can see me moving around. If you're on the WebEx right now, all you're doing is seeing a PowerPoint. And we've got a copy of the PowerPoint that you can download. And even if you're doing the live stream, if you're like me, I don't have great eyesight, so I'd rather look at it on my computer screen. So what's the goal in testing? And those of you that do a lot of presentations and you probably spend your life experiencing death by PowerPoint is, you put a bunch of words up there, but the main thing I want to focus on is this little bottom paragraph. And very simply, the goal in testing is to help us make integrity decisions by improving our ability to model pipeline defects. And I think most of you on this call, you're in the pipeline industry. I've been there for most of my career. I love the pipeline industry. I enjoy the people. I enjoy the kind of challenges that we have. But what we're trying to do eventually is get to a point, and this is a point in the future, I'm going to say probably 10, 15 years out, where you run an inline inspection tool and it categorizes the features. You've got all these models that perform an assessment, okay, and then you determine if you need to repair a particular feature At some point, and it sounds crazy, but at some point, you'll push a button or it will automate the process, and then you'll have some kind of robotic structure that will go out, it'll excavate the pipeline, and you'll be able to make a repair. So I don't think computers are going to completely take over the world. I'm not talking about a Terminator experience here, but I am talking about that we're going to automate this process. And I know if you go to any pipeline conference, there's a lot of people talking about AI and machine learning, those kind of things. We're going to get to that point. And so a lot of what we're talking about today is to make those models extremely intelligent. So a little bit of a rabbit trail. If you think about if you're a parent, and we've got 3 kids, and they come and they get this little package, you come home from the hospital and you're trying to figure out as a new parent what to do. It's amazing how you learn along with the child. And then the child learns how to walk, and they start talking, and they're just like a little sponge. They're constantly absorbing that information. That's what we're talking about here. We're talking about these models getting smarter as they get older and we get more data that's feeding into it. So as we go through this presentation, don't leave this thought. Just continue to think about it in the back of your mind as we talk about how do we take all this information. Now, I'm an engineer. I like equations. I like to get my calculator out at least a couple of times a day and just prove to myself I still can do basic math. This is not rocket science. I've got a 5th grader upstairs who's probably finished his homework hopefully by now so he can play video games this afternoon. But I guarantee you, if I sat down with Aaron tonight, we could go through and we could do these equations. It's not overly complicated. But this is a safety moment. Those of us in the oil and gas industry, every time we have a meeting, we always talk about safety. So today's safety moment is energy level, stored energy. And in our world, anytime we do a burst test, we always calculate the stored energy. And I'll admit, when I was at A&M, we didn't talk a whole lot about this. So if I'm doing a pressure test with water, there's an equation here, and you can get on the internet, you can find it. It's pretty simple. It's just 1/2 times the pressure squared times volume divided by the compressibility of water, which is about 330,000 psi. I promise you this is the only slide that has any equations because I don't want to lose the audience. Get a bunch of differential equations and you lose everybody. So this is the energy for water. We do a lot of burst tests on 12-inch pipe. And typically the pipes fill at about 4,000 psi. If you run through that, the amount of energy that's stored in that sample at 4,000 psi is around 20,000 foot-pounds. Specifically, it's 22,000. So if you envision, if I was able to take 1,000 pounds and drop it from 22 feet, that's the kind of energy level we're talking about. Now, if I take that same sample though, pull the water out, and I stick nitrogen or stick a gas in there. Let's say nitrogen is probably the best one. I think that's probably the numbers that I ran. I do the exact same burst test. The amount of energy that's stored due to the compressibility of gas is 330 times what it is with water. And it's kind of fun to express it in terms of pounds of TNT. That's about 5 pounds of TNT. So every now and then we'll have people that come to our lab, and one of the questions is, do you use water or do you use gas? And being someone that does this for a living, it always scares me a little bit when people ask that question, because for what we're doing, there's no reason that we need to do anything most of the time other than with water. When we're just doing basic qualification tests of composites, there's no reason to get complicated. Now, the reason I mention this, there's 2 things. Number one, you've learned something today. My guess is most of you have not seen these equations, and if you have, it's been a long time. But the other reason is that we think a lot about safety. And so before we do a test, we make sure the energy levels that we're going to be testing with, that we can safely do those. And I'm happy to report for the vast majority of pipeline testing that we do, we've got the facilities to do that. We did do a gas test about 1.5 years ago, and we did it at another facility. Everything went great. But in our shop, we're not going to be doing burst tests with gas. Okay, so let's do the virtual lab tour. I really kind of enjoy this. So those of you that know us, we moved in the first part of 2019. This is literally what our lab looked like. It's just a big warehouse out in Waller. We've added air conditioning. We've had all kinds of equipment. I need a picture that shows what it looks like today. It's completely filled up. Sometimes we've got 15 to 20 people in there. There's a lot of activity going on. But I have to remind myself, this is what it started when we got going. We've got about 4 acres, so we've got land to bury things. We've done a couple of projects where we buried samples, and it's just really been a great little home for us as we've started to build this business. Obviously, a lot of what we do is burst testing. We also do pressure cycle testing, and we've done some pretty good sized burst tests. I think we did one at 36-inch pipe sample last year, bursted probably a little over a couple thousand PSI, so pretty high energy levels, and this allows us to do things very safely. We've also done some bend testing, and so the vast majority of what we're doing is pressure, but from time to time we get asked, can you take a pipe and bend it? So can you do something with wrinkle bends? Can you do something with girth welds? And so we basically built this rig. Those of you who know Corey Duncan, Corey's great at designing, and Chance Deneau, who worked with me in putting this presentation together, they designed the load frame, and we ran calculations. We ran, I think, 5 or 6 tests last year, and everything went great. Everything's working the way it's supposed to. I had to include this photo on the bottom. We've got a 3D printer, and really proud of our guys I've always wanted to have one of those, and so we figured out how to use it. So we made a little model of it, so next time we can actually get out and go to a show, we're going to bring that with us in the booth, and people can kind of see. It's kind of hard to load this thing in the back of your pickup truck because it does 3 million foot-pounds, and we can do very long samples. The other thing we do the 3D printing, though, is sometimes we'll make little fixtures in the lab. If we need something to hold a LVDT or a displacement transducer. So really proud of the guys for using this resource just kind of as part of our daily operation in the lab. Some of the other things that we do, those of you that are familiar with ADV, we do a lot of work in the composite space. And so we'll do cold temperature things, we'll do elevated temperature. So we actually built a box, Corey designed it for us, and we did a pressure test down to minus 51 degrees Fahrenheit. So very cold temperature. We've also done some composite work all the way up to 60 C or 140 F. So we've got the ability to kind of simulate different environments. So it's nice to be able to do that. It takes a lot of work to get to that point. One of the things that you notice here is that this box here is on rails, and so we load the sample in there, and then we push it into the box, which is insulated, and allows us basically to cool that. But from a structural safety standpoint, this steel box is the one that's taking all the load, when you have a failure. One of the other projects we're doing, those of you that know me know I love joint industry programs. Did my first JIP about 15 years ago on my PhD, and I think we've probably done 20, and we have a handful going right now. This is a spoolable pipe JIP. We started it late 2018, and one of the operators came to us and said, look, we'd like to do a JIP. We know you like JIP, so we reached out to a group of operators and manufacturers. Last count, I think we've got 6 operators. ConocoPhillips joined last week, and then we've got 8 technology companies that we're evaluating their technology. So what we're doing, we built these rigs, and we displace the pipe, and we're basically, the purpose of this JIP is we're looking at the connection. And so we displace the pipe, we hold it in place, hold it under pressure at 1500 PSI, which is the design pressure for these spoolables, 4-inch diameter, hold it for 1,000 hours. Everything looks good at that point. Then we induce 100,000 pressure cycles all the way up to 1,500 back down to around 100 PSI, and we just sit there and cycle. And then if they survive and we've finished a round, then we basically do a burst test in this position. So we finished our first round. We have several more rounds. We'll be probably running these for the next 5 to 6 months. So everything's going great. The reason I mentioned JIPs, it's a great way to leverage money. And so the operators come in and they put, say they put $50,000 or $100,000 in, and you get a group of operators, you get a group of technology companies coming together. So for a single investment of $50,000 to $100,000, you can get an overall program that's $500,000 to $1 million. So they take a lot of work on the consulting side to kind of get everybody together. If you're in management, you know as well as I do, sometimes engineers are not easy to manage because we're all smart and we think we know better than everybody else. And I'm not saying this JIP was that way, but a lot of times JIPs can be difficult in getting everybody on the same page. The other challenge is always contracts. And I will admit, when I was at A&M, I don't think I had a professor ever even mention a contract, but that's a big part of what we do in the oil and gas industry. So hopefully all of this is making sense. One of the other things that we did, we bought a little Tinius Olson. This little load frame will do about 120,000 pounds. We've got a little wrinkle bend sample. We've been doing a lot of composite work, so we can actually put our samples in there and we pull them. This unit's hydraulic, and what it allows us to do is do fatigue testing. And so we can load a sample in there, we can go back and forth and generate fatigue data. Really excited about this, having the ability to do this. And if a client comes to us and says, look, we want to do some fatigue testing on this material, we've got the equipment to be able to do that. One of the other things that we do from time to time, we'll just do, I think the Brits call it bespoke. And so we'll build little load frames for a specific purpose. And so this is a little load frame that we built just to put dents in pipes. And I will admit my very first project when I got out of graduate school at A&M, first big project was working on dents. And so we put dents in pipelines. And so what we do is we take a hydraulic cylinder. It's not overly complicated, but it's really effective. And you push the indenter down. You hold the indenter in place while you pressurize it, so you get a lot of plasticity. And then you create a dent. And then you take the pressure off, you pull the indenter out. And most of the time what we're concerned with when we talk about dents is we're concerned about pressure cycling. So we'll go up to 72% smice, and then we'll just sit there. As I say in West Texas, we cycle till the cows come home. And so we get a lot of fatigue data. Eventually we get a crack, and this is a textbook crack. Anytime you see a strain gauge, which is what this is, it's running right on top of where a crack is, you know that you've measured exactly what you want to measure, so we're getting high strains. And this is one of our samples in our green box. And then we also had a project for an operator where they sent us some ILI data, some caliper data, and we built a FEA model of it. So we're able to kind of get correlation. Once again, I talked about the goal in testing is to make the models smarter, to make the models or they're better predictors of the kind of things that we want to see. Once we get all that data generated, how do we make decisions? There's a lot of data acquisition. We've got some really smart guys that are working at ADV, and they know how to hook the equipment up. You got data acquisition, you've got all of these sensors, and in the test lab world, this is it. If you run a test and you get good data, you got information that you can use and really make good decisions. So I'll put this graph up. This is one of the projects that we did work on, and actually it's our 4th case study. So Chance and I were looking at all the data, and I was like, okay, Chance, what's it saying? And so he spent some time. Sometimes it takes a week or 2 weeks to kind of process what patterns are we looking at. But I'll be honest with you, when we first looked at this data, this is what I was thinking. What in the world is this telling us? One of my favorite sayings is if you torture the data long enough, it eventually confesses. And so this data eventually confessed, and it told us a story that we did. So this is one of those things, when you come into an environment like what we're doing, you need seasoned engineers. For young engineers, it's difficult to take all this data and what do the patterns mean. What's really interesting, without going into too much detail, the challenge in this is we had 24-inch pipe, and if you know anything about large diameter pipe, it always has some ovality in it. So if I put strain gauges every 90 degrees and I pressurize up, it's not going to be uniform all the way around. Now, a young engineer who's just right out of school probably wouldn't know that, but if you've been doing things for 20 years or longer like I have, you're always looking for things like ovality that affect it. So anyway, this is just a great example. This next slide is actually a new slide, and I don't know if you can see, but this is an example of our lab schedule. And I consider myself relatively organized. I think the word that we use sometimes is anal, that you like things to be structured. And when I get flustered, like if you were early on when the WebEx wasn't working, I get a little flustered, which is probably why I couldn't have been a fighter pilot. So I thought I was pretty anal. I think my mom's watching, and she counted my Legos as a child, so I'll give her a little shout out for that. But Corey Duncan, who manages our lab, he is organized way beyond what I'm doing. And so this is just an example on one project that we're doing that we've got people assigned. You can see initials. So I love that. Corey lives in that little world. And so when you work with us, recognize that we've got a lab schedule. We have this thing mapped out for sometimes months in terms of assignment and how things are going. So I'm really proud of just the overall organization that we have. And I'm certainly not going to take credit for it because I didn't develop that. So one of the reasons that you're probably here is for us to talk a little bit about case studies. So this is, as I said, to me, when I'm listening to a speaker, whether it's a preacher and they start telling stories, that's what engages me as an audience. So I hope you enjoy these case studies. One of the things that's a major issue, and I think it's a major issue whether you're upstream, midstream, or downstream, but it's cracks. And I have a fair number of friends who do work in the downstream industry in the refineries. And so they'll have some vessel that gets a crack in it, and they don't want to shut it down until the next turnaround. So there's a lot of inspection work that goes on, and they figure out what's the geometry of the crack. They'll run models and do calculations based on fracture mechanics to say, you know what, we can continue to operate this thing for another 6 months, so we're going to be good. So a lot of what we're doing pretty much from day one when we started the lab early last year is we're putting a lot of cracks in pipe. And so the way it starts, if you're looking at low frequency ERW, is you take a piece of pipe and you basically you etch that surface and you're looking for that bond line. And so once you find that bond line, then you put an EDM notch, and this is a little machine that illustrates putting an EDM notch into that seam, and then you do some pressure cycling. So this case study just kind of walks you through the process that we do to create cracks in pipe. One of the challenges in the pipeline industry right now is we just don't have enough real-world features. So what that means on our side of the testing side, sometimes we have to recreate those. And so there's a certain art to it. There's certainly a science, but some of it's just a good old experience in knowing how to do this. So if you're familiar with the pipeline industry and you're familiar with low-frequency ERW pipe, if I showed you a photo of that and I'd say, what caused that? You say, well, there's probably some kind of feature in the seam, but you notice how it opened right up. And so that's a classic example of a seam weld feature, and it just opened up. If this thing was miles long and you had gas, you can literally open up. It's like a zipper. It would just open up for very long distances. One of the things that we're going to talk about today, and I've spent most of my career starting in 1994 working on composite repair. So this is a composite repair technology. It's a carbon system. It's actually made by CSNRI. Originally it was Milliken's Atlas carbon system. And so we've done a lot of testing on that, reinforcing planar defects and cracks. We're even doing work right now on leak repair. So it's a really, really solid technology. So what you notice here is we had a feature underneath it, but when we did the burst test, it failed outside the feature. So when these composite systems are designed well, they're installed, it's amazing what they're able to do. So one of the things I want to point out right here, if you notice in this image here on the left, is we have an EDM notch, and it's interesting, to the naked eye, it looks very, very sharp, but when you zoom in on a microscope and you do a macrograph, you notice that it's very round. So when we do the pressure cycling, we wind up creating a notch. The notch turns into a crack. So that's a lot of what we're doing right now. Probably in the next 6 months, we're probably going to make well over 100 of these on a couple of different projects. And so we've got some technologies that allow us to monitor that. One of the questions in the pipeline industry right now is, what's the accuracy level of the inspection technologies that we have? So we're doing a project looking at computed tomography. There's several companies out there. Inspection Associates has a field deployable tool. And so we're going to talk a little bit about some work that we did with them. So we took a pipe sample, 12-inch. We put some EDM notches in it. We did the pre-cycling to generate cracks. And then we sent it over to Inspection Associates, and they did their magic and they did some inspection work. Then we got the pipe back, and we broke all of these notches open to see what kind of crack growth that we had, and we compared them against what Inspection Associates had determined. And what we found was there was really good correlation. You'll see that here in a couple of minutes. And so as we're doing the cycling, we have a couple of different ways. We use clip gauges. DC potential drop is another technique that can be used. You can also use strain gauges. So what we're doing is we're looking at that notch as it opens up, as the compliance in the notch changes, and we start growing a crack, you see the strain really start growing. And so we've kind of developed some techniques that once it starts growing, then we stop the test and we know that we have a crack that's formed. And so here's the three samples in this program. We had multiple features in each of the pipe samples. So as I alluded to earlier, at some point we broke them open. And I'm not sure if you can see it on your computer screen, but there basically was an EDM notch, and we call this the starter notch, and then we cycled. If you've done any work in fatigue, the typical pattern that you get is you get kind of an elliptical shape that develops. And so that's exactly what we see here. The EDM notch was flat bottom, but once we start cycling this rusted area, you see the growth, okay, of the fatigue. And so you got this notch that turns into a crack. We sectioned it, and so this view image on the right is I'm looking down the axis of the pipe, and what you notice is this EDM notch has turned into a crack. And so it's relatively easy in one sense to see a notch. A very tight crack like this is definitely more of a challenge. And so this next slide, we're kind of comparing what we get under a microscope. To the right, we have the images from the computed tomography. And so we broke a bunch of features open, we did a comparison, and then basically we created a plot that showed what did we measure versus what do we really have. And that's what this graph shows. So those of you who've done any kind of statistics, you do what's called a unity plot. And so you just draw a straight line, and so we're measuring all the way from 0.4 inches. The pipe wall here was 0.375, so we actually had one feature that went all the way through. and you see these dots, there's actually a paper that we can get to you. If you send me an email, I'll send you a copy of it. It was presented at the PPIM conference here in February, here in Houston this past February. And we had a paper where we talked about all this, so you can really look at the data. So to me, this is a great little case study. It has multiple features. We're looking at a new technology and we're evaluating it, but we're also looking at cracks, which I'm convinced is going to continue to be a big part of what we're doing in the pipeline industry. So the next project is one that we did. It was, I think, probably my first GIP when we started ADV, and it was looking at steel sleeves. So we had 4 pipeline operators, and Allen Edwards, you see their logo down here on the bottom, and we basically were looking at using rolled plate, okay, or foreign manufactured sleeves. How do they perform against pre-tested pipe? And as this first bullet talks about 192, which is the gas, CFR 195, which is the regulations for liquid operators. Some operators interpret those regulations as requiring pre-tested pipe. And what's interesting is Tommy Preck, who's with Allen Edwards, he and I flew up to DC in the latter part of 2017, if I recollect, and we visited with the regulators, and they said, look, as long as you're showing us through performance that these technologies, if you will, these steel sleeves perform, that's what we're looking at. And so this program was a great example of kind of looking at it, what I'll say an older technology. Steel sleeves are certainly not a new technology, but we looked at them in a different light, and we partnered with the operators, and now they're able to use these manufactured sleeves from Allen Edwards with confidence. And so we did a JIP look, and we did some full-scale testing. And so this is kind of the matrix. We had corrosion features, we had plane dents, we had unreinforced features that were kind of our base case, and then we also had 2 of the corrosion repaired and 2 plane dents. And once again, we've got a paper that we presented at PPIM in 2019 that we'd be glad to share with you if you're interested. So these are a couple of photos. We put dents in using the same process we showed earlier. I think we actually painted our rig since then, but you can see this is kind of pre-painted. This is Harry Ludwig at PT Welding, who's made many samples for me over certainly the past decade. And so we've got strain gauges here, and this is Chip Edwards, who's president of Allen Edwards. So he's holding the wires as we lower this sleeve onto the pipe, and then we weld it up. And so those strain gauges are very important because what they do is they tell us what's going on underneath the steel sleeve in the dent. And so great program, done a lot of these, and after a while you kind of get a pattern, and it seemed to work very well. So as I alluded to earlier, we had a lot of strain gauges, and so we're putting strain gauges in the feature on the base pipe. One of the challenges when you put a steel sleeve or even a composite is, how do I get that information from on the sleeve to outside the sleeve? So we always have wires running out. In the early days when we started doing this work on composites, there was a question from some of the composite manufacturers who said, is this going to affect our performance? And we ran a lot of tests, and we really convinced ourselves that these little bitty small wires that are coming out from strain gauges don't have a significant effect on the structural reinforcement. Now, if we're doing leak repair, you better believe that would have an effect. So anytime we're doing leak repair testing, we don't put strain gauges in these features because it's basically a leak path for water or some kind of medium coming out. So this just gives you an idea of the instrumentation that we have on these samples. Very, very important. This is kind of a summary of results. I don't expect you to see it. If you download it off the website, you can look specifically at the numbers. But what we mainly showed is that you get a significant increase in fatigue life over corrosion and dents when you repair it versus when you don't repair it. And so that was the main thing that the operators that participated in this JIP, they're like, just demonstrate to us that this works. The good news is all the operators who participated for the most part operate gas pipelines. And gas pipelines, unlike liquid pipelines, don't see a lot of cycles. But if we had done a burst test as opposed to fatigue testing, this program wouldn't have been very useful, because if you repair a dent, you do a burst test, more than likely, unless it has some kind of crack already in the dent, it's not going to fail in that. So fatigue testing is definitely a better way of doing these. And these are some strain gauge results. As I alluded to earlier, anytime you get a crack that runs underneath the strain gauge, this is the dent, failed in about 22,000 cycles. That fatigue crack ran right through the strain gauge. So what that shows us is, as I'm increasing my number of cycles, okay, the strain in the dent's going up. What I like in this graph, though, when you look at the yellow and the gray, is that the steel sleeve is keeping that strain consistent and relatively low. You know, I think that the maximum was about 4,000 microstrain. From my experience, it kind of goes back to some work I did on my PhD. If you can keep the strain in the steel below about 4,000 microstrain, you can have extremely long fatigue lives. And so I've written some papers on that. So if that's something you're really interested in, just shoot me an email and I'll be glad to visit with you about it. So kind of the conclusion is, you know, this performance-based test program demonstrated that Allen Edwards manufactured sleeves do exactly like they've been communicating. And once again, this goes back to Ronald Reagan's quote, "Trust but verify." And so the nice thing for Allen Edwards, anytime they go someplace, they can, you know, plot this report down or this paper that we've written, and they can demonstrate to industry that these steel sleeves perform exactly the way that we want them to. Okay, let's shift gears a little bit. And those of you that know me know I love composites, just got early on in my career. So I thought I'd share with you some data literally that's hot off the press. We're doing some tests right now. We got the 1,000-hour test started this morning. So we're working with Omega Wrap, and they're developing a carbon and an e-glass technologies. They're using epoxy as the resin. And so as I alluded to earlier, we've done a bunch of tensile tests in our little Tenius-Olson machine. And we got an e-glass that's got an ultimate tensile strength of about 80,000 or 80 KSI, 80,000 PSI. The carbon's around 110. We've had some numbers that are way higher than that, but these we felt like these were numbers that were pretty representative of the mean with some confidence levels. If you're familiar with this part of the industry, there's a standard called ASME PCC-2, which stands for post-construction. And all of the composite repair technologies that are used in the pipeline industry and to a large extent even in the refineries and the downstream industry, we're using this standard to provide a reference. And so back 25 years ago, we didn't have a standard. So to me, it's wonderful to be able to take a standard and for everybody able to have a specific list of tests. So what I'm going to show you today is a couple of tests that we've run in looking at this standard and how do we meet the requirements of the standard. So I guess it was probably last week, Tommy Precht and John Rickard and Tyler Fairclough came over, and we had some samples that we had made, and we had a machine defect that's, you can't tell, but that's 75% deep. And so it's a very thin wall. It's a 375, so there's not much left. There's about, I think, 093 left. And so we put a couple of strain gauges on there, and so that's kind of step one. Step two is you put what's called a load transfer. Some people call it a filler material, and it's kind of an incompressible material. It's, you know, it's a little bit like Bondo. I hate even saying that because you can go to High-Low or some auto parts store and get Bondo, but this is a high-tech Bondo that's got a very high level of compressibility. You mix it up, you put it in the corrosion area, and you see us smoothing it out. And then in step 6, then we start saturating the cloth. And then once we saturate the cloth all the way down here in 8, you see us wrapping it around. This is called the spool survival test, and it has a relatively thin wrap. If we were doing this out in the field, would have probably something that's closer to 3/4 of an inch. But these repairs are relatively thin. They're typically less than 1/4 of an inch because what we're going to do is we're going to pressurize, and we want to make sure that material and the filler material all work together and get us to a minimum pressure. So that's what happens. We let it cure for a day or so, and then we basically do a pressure test. So what you see here on the left is the e-glass system. The yield strength on this material, in order for us to get to the yield strength, the actual yield strength of this material, we had to get to about 2,800 PSI. And so what you see down here on the bottom is we got to 3,379, so almost 3,400 PSI. And you wind up having, at least in this one, wind up having a leak underneath it. So the bottom line, we got all the way up to pressure. On the right side, you can see we actually had a failure. It got to 3,700 PSI. So we almost got 1,000 PSI higher than we had to. And this is extremely thin. I mean, this is definitely less than 1/4 of an inch. So anyway, the good news is you check that box and you move on to the next step. So actually what we're doing today, we're putting, we've got 3 samples of the e-glass and 3 of the carbon, and we are putting them under a very high pressure for 1,000 hours, which is about 41 days. So we got a big box in our shop. We dropped them in there, and we're just gonna, you know, put them in there, and then we'll come back about a little over a month, and we'll pull them out and check them out, and everything will look good. And then that allows us to do a lot of the other work. So I alluded to earlier, we put some strain gauges on, so we go all the way up to the target pressure. We drop the pressure all the way down, and the fact that these curves don't go all the way back down to zero means that we introduce plasticity in that simulated corrosion region. And so you got 10 to 15,000 microstrain. 10,000 microstrain is 1%. So what that means is we plastically deformed it, we come all the way down, and then we go back up, and then we go all the way to burst. So there's a couple of good things you see here. Number one, we got to very high pressure. The other is, even after you go all the way down, this is called a hysteresis loop, even though it'll go all the way down to pressure, that composite is still able to provide reinforcement and go all the way. Now, PCC2 doesn't require that you go to failure, but I hate for a client to spend as much money as Alan Edwards is doing in funding Omega Wrap, and for us not to do a full-scale destructive test. It tells us what that limit is. And so, you know, the whole purpose of this presentation is to talk about full-scale testing. And full-scale testing, you're pushing things to the limit. It's kind of like going to a doctor and taking a stress test. He's going to put you on a treadmill. He's going to run you and see what you can do. That's exactly what we're doing with Omega Wrap. We're going to push it to as far as it can go so that when we put it on your pipeline system, that it's going to perform the way that we expect. So anyway, I thought this was, as I said, kind of hot off the press. It was timely. And it's the kind of thing that I think industry needs to see when we're evaluating these technologies. So the last case study I've got is a study where we worked with PRCI, and you see I've got their logo down here. A little bit of a rabbit trail. PRCI stands for Pipeline Research Council International. It was started in the late 1950s, and a group of primarily gas pipeline companies got together and they began to fund research. So it's kind of like the ultimate JIP. Cliff Johnson's president of PRCI, and they've done a great job really bringing the whole pipeline community together. We've got liquid operators, gas operators, you got consultants like me that come. And matter of fact, the last time we all got out of town was San Diego. They have an annual research exchange, so I'm really thankful we're all able to see each other. At some point, we'll get out of our houses and go see each other again. But this is a presentation, this part of the presentation I did actually at the REX meeting. So one of the challenges when you've got a pipeline system is you identify an area, maybe you've got a valve, and you need to work on that valve, maybe you need to replace it. How do I go work on that pipeline section without blowing the whole pipeline down? And so it sounds like no big deal, but if you've got 25 or 30 miles that you have to blow down, if the pipeline's big enough, you could be talking about hundreds of thousands of gas, thousands of dollars of natural gas that I have to blow down. So is there a technology out there that allows me to block the pressure on one side, bleed off on the other? So this is called basically a double block and bleed. So I've got two plugs that I put in place and I bleed the pressure. So it's double block and I'm bleeding it off in between. So the next couple of slides will walk you through this process. So David Zhu with PG&E, some of you on this call know David, and David was kind of the godfather in a sense of this project, and he approached me and said, Chris, we want to do a project, we want to look at some technologies. I know you like JIPs, so reach out to some of the technology companies, and let's do a PRCI project with the technology companies. Now, offshore, this technology is used quite a bit, but the difference between an onshore and an offshore pipelines tend to be thicker, especially deep water pipelines, because you've got a very high level of external pressure, so you make the wall thick so that it doesn't collapse. On onshore, we don't have to worry about that. These pipelines are buried, but you're not seeing a lot of external pressure. And a good rule of thumb for external pressure, and it's off a little bit, I'm probably within 15%, but it's about half a pound per square inch for every foot of water depth. So for example, if I go to 4,000 foot water depth, the external pressure is roughly about 2,000 psi. So I have to design my pipeline system to do that. So the advantage for these tools going deep water is that when they seat, they don't have to worry about generating high stresses in the pipeline because the wall is relatively thick. Well, I'm going to shift gears now. I'm going to come onshore, and I don't have thick wall. I may have a 24-inch pipe that's got a 1/4-inch wall. So when I seat these tools, am I going to generate a very high level of stress? So that was the whole purpose of this program, was can we use these tools onshore? And I'm happy to report the results were actually really, really good. So one of the things that David wanted to do at the very beginning was he wanted to run some FEA models. And so he said, Chris, I want to do modeling, and I want to validate the models, and then I want you to build me an Excel spreadsheet that I can plug in my pipe diameter, my wall thickness, the pressure I want to go to, and it tells me, am I safely operating this pressure with this tool in place? So anyway, the program took about 2 years, but we started off with the FEA. And so this is an example of one of the tools. There were basically 3 companies that participated. PPIG, which stands for Pipeline Pressure Isolation Group. In the pipeline industry, kind of like the military, we love acronyms. And so sometimes I apologize if I've said some acronyms that you're not familiar with, but this is PPIG. We also engaged TDW and STATS. And TDW and STATS have been doing this for a long time, primarily offshore. So we got all 3 of these companies. They all did very well. So we basically built FEA models, and we estimated what the loads that were generated by these tools, because they expand in place. So it's kind of like a packer, if you're familiar with that. So you send the packer down, you seat it, and so you have some mechanical seals that bite into the pipe. And so we've got a high pressure side, a low pressure side. So this is where we started. And so we did some FEA modeling. Overall, the results were very good. So the question was, let's validate this. So we went to the lab, and we took some 24-inch pipe. We ordered flanges. And this little schematic here gives you a good idea of what we're doing. So we have the center section that basically we replace. So we'd run PPIG, then we'd cut that section out, then we'd bring TDW in, and they got a fresh pipe. And we would put strain gauges depending on how their tool was set up. So each of these 3 technology companies, they had a little different way of, mechanically locking in or sealing. So we needed to make sure that the strains that we were measuring reflected what we wanted for each of those tools. So this is one of the tools that came in. We put it in place. We pressurized one side. Okay, so we had the high pressure side. The tools in here. What we don't want to see on this side is pressure. And I'm happy to report all 3 of them did exactly like they're supposed to. These tools also, I didn't mention this early on, they drop these tools maybe in a pig trap, and so they run them down, okay, and then they remotely set the tool. And so this is all done above ground, and so there's a lot of technology just learning how to communicate with each of those tools. And so we ran it, and then we processed the data. And if you remember, I showed that graph a minute ago that we had all the strain gauge results all over the place. So we spent some time trying to get sense of all that data. How does that compare to what we're seeing in the finite element models? And so I don't have time to go into all the details, but we were able to build an Excel spreadsheet that used these calibrated FEA models. One of the other things that was a concern was when I had these tools, what kind of damage do I possibly inflict to the ID of the pipe? So after each of the tests, we sectioned, and John Rickard, who works with us, did a great job sectioning and figuring out where the maximum deformed areas were on the ID of the pipe. And so this is one of the images that shows you where we cut. And so, I was going into this, I wasn't sure what to expect. Sometimes as a consultant, you get involved in a project, and the technology company that you're working with, they know their technology better than anybody in the world. And as a consultant, you're coming in, and I tend to be very optimistic. I think things are going to work. But I was really pleased with the minimum level of deformation that we saw. And so you can see there's some marks there. But in terms of the overall, from an integrity standpoint, certainly for gas pipelines, which is most of the companies that sponsor this program were looking from a natural gas standpoint. And even if you had a liquid pipeline, these little features, you'd have to put a lot of pressure cycles to get those things to grow. So overall, I think it was a great example of using numerical modeling. And remember when we started talking, the goal is to make the models smarter, make the models better. Then we did full-scale testing. Then we went back and we calibrated our models to make sure that they were spot on. And then we added a little metallurgy on top of it just to make sure that what we're doing to the inside of the pipe is something that everybody's comfortable with. So I even got an email from one of the operators yesterday who said, tell me a little bit about this program. And so I was able to get him a copy of the report. In a lot of these research programs, and I will admit when I was at A&M, being an engineer, I didn't necessarily love writing. I actually really enjoy it today, but a lot of what we do is we write reports. And so we're not just running tests and sending Excel spreadsheets and things to clients. We spend a lot of time writing these reports so that when it's sent to you as an operator or technology company, that you've got news you can use, you have information that basically helps you make decisions through all the work that we've done. So kind of wrapping it up, we really enjoyed the opportunity to spend some time with you this afternoon. I really like the live stream. kind of compared to the WebEx or Zoom. After a while, I call it the Brady Bunch syndrome. You log on there and you see everybody's head, and I think we probably all spend a lot of time doing that. I really like the live stream. I feel like I'm not seeing you, but in a sense, I feel like I'm talking to an audience instead of a computer screen. So this is kind of closing remarks. So last year we had a great year. For the most part, I'm living the American dream. Able to start a company, put engineering to work with a lot of really good, bright people, and I'm completely fine with not being the smartest guy in the room. We've got some really bright people, and just solving challenging problems. So as I said, for the most part, this has been an incredible experience. And so we worked for 43 companies last year, and of those 43, 15 were operators. And so actually I was kind of tweaking slides last night, and I just grabbed this from our website. There's a lot of people. And at the end of the day, without getting a little too altruistic, business is about people. And so when I'm talking to someone on the phone, I think I had 5 or 6 phone conversations this morning. There's somebody on the other end of the phone. There's somebody on the other end of the email. We take that seriously. If you need someone to do something and it means that we need to stay up all night to do that, we're in the service business. And it goes back to Tillman Fertitta's. It's the 95-5. It's that extra 5%. And so what kind of as president, I really focus on that 5% because I want us to be good at that. And the good news is, everybody who's working at ADV, we're all on the same page there. We don't argue about that point. I love testing. I love modeling. My career, I've built thousands of finite element models. I've done thousands of tests. It's not an or, it's an and. You don't just do testing. You don't just do analysis. They work very well together. And one of the things that we're really working on is the fracture mechanics side. And fracture mechanics, for the most part, is talked a little bit about in the engineering program, sometimes if you go to graduate school. So that's an area we're focusing on right now. We're developing some expertise in that space on the testing side, as well as marrying it with the analysis side. And then it's great for technology validation. As I talked about earlier, if you got 15 operators, that's about a third, 2/3 of the companies that we're working with are technology companies. And so testing is a great way to prove that things that work. If they don't work as expected, the beauty in the lab is you can go back and you rerun a test and you can tweak things. My personal bent is I'd rather have technology validated in a test lab than go out in the field and try to make sure that it's working.